Okay, welcome everyone. Happy Pi Day. So delightful for me to be here back on home stomping ground where I did my PhD. I'm here to introduce the wonderful and amazing Katherine Seaton and also launch the annual CARMA-MATRIX Maths Art poster competition. So we haven't had an official launch before. Hey, wonderful to see you. But we decided it'd be a good time to have a launch, and definitely a good day to have it on Pi Day. The previous uni I was at was Newcastle. We always used to have pies on Pi Day, pie reciting competitions, lots of fun. I was missing it, and I thought, what a good day to do this on. CARMA has done a lot of sort of promoting the interaction between maths and art and different aspects of culture. And one of the parts of that has been the arts poster competition. It was instigated by Ria Agarwal, who was a student at the time at Newcastle. She said, I'm in engineering and maths, and the engineers always get to do fun stuff, but us mathematicians, we're boring. We need to do more fun stuff. And so that was the start of the competition. Encourage anyone who would like, the competition is now, David Ellingham confirmed, open, so you can start submitting your entries. And there's a lot of beautiful stuff you can see. If you look at the previous years, I'm not going to spoil Catherine's thunder too much because I know that she has got some examples of it in her talk. But I'll show you my favourite, even though it didn't win in that given year. That was, if it'll go there, maybe it won't, maybe you'll have to look on your own. That was Asher Rao's beautiful textile artwork. Oh, well, there's one from Kate Smith-Miles, who is a Melbourne Uni person, so that's an appropriate one as well. But feel free to have a look at some stage. I also want to acknowledge Matrix and CARMA's partnership with Matrix. I remember when Australia didn't have a National Maths Institute, and I know how important Matrix is, and I know how appreciated it has been by the whole community, and how appreciated it was also by John Borwine, who was the founding director of CARMA. And I remember him talking about what a big and broad impact it had. So I'm really proud that CARMA partners with Matrix on this. And I better quickly introduce Katherine and then let her take the stage because she's wonderful. Her contributions span statistical mechanics. She's in the statistical mechanics group here. Educational research, some really insightful stuff about assessment, some stuff about social side of maths and art. She is an artist and a mathematician, and I welcome Katherine to come and give us a beautiful Pi Day talk now. Oh, and we press control. That's it.
We did it. Thank you very much, Judy. And I'm a bit scared because Judy Ann always says those things and then I have to live up to it. So yes, mathematics, art and creativity is the title for today's talk. And I won't tell you too much about this image that you're looking at here, but I will tell you that it is from last year's CARMA-MATRIX Art competition. CARMA-MATRIX. It's in many words, CARMA-MATRIX Maths Art competition. So I promised you an evening stroll past a variety of art forms with a taste of pie. Because it is, of course, Pi Day, 3rd month, 14th day. And the origin of the Pi Day celebration seemed to have been traced to a place called the Exploratorium, which is a science museum in San Francisco, where indeed there was pie eating. People walked around in circles reciting the digits of pi. So, you know, you can all be thankful that I didn't propose that for this afternoon. And then in 2019, the decision was made by UNESCO, which the International Mathematical Union and UNESCO. So UNESCO is United Nations Education Culture Organization, to proclaim Pi Day instead to be called the International Day of Mathematics, November 2019. So you can just imagine that when the first one of these rolled around in March 2020, it was a little bit sad, wasn't it? And in fact, I was supposed to go to Newcastle to do a big Pi Day thing with Judy Ann that year, and I wasn't allowed to fly because it was the 14th of March. And on the 16th of March, my university, like everybody else's university, closed their doors for a while. One of the features about making it the International Mathematics Day of Mathematics rather than just Pi Day is that they've opened up the themes to explore wider themes rather than simply eating pie and reciting the digits of pi. And the theme for this year is mathematics, art, and creativity. So we're going to look at pi in a few different ways, and then we're going to sort of move on to looking at mathematical art. So this is a piece that won last year, and it won the CARMA-MATRIX Maths Art competition last year, and it's called Prismatic Parchment of Pi. And we can see the symbol in there. I like it. You don't have to. I went to an art opening last night and they told me you don't have to like art. You just have to, you look at it and you can like it or not like it. It doesn't matter. But I mean, I do like this one, but it maybe doesn't help us visualize much about pi to start off with. So I brought along this so we can visualize pi with this. This is a tube, contains 3 tennis balls. So the height of it is 3 diameters high. So it's 6r. But we know the circumference of this tube is 2 pi r. And we haven't talked about how big pi is yet, but when you think about it, pi is actually a bit bigger than 3. So it's further around this tube than it is tall, which I always think is just amazing, actually. Okay. So that's the first thing we all know about pi, right? 2 pi r, the circumference of a circle. So let's get back to the pies. Where did the pies get in? Why does Judy-Ann and Tom want to feed us pies today? Well, it's a homophone in English. They sound the same. The way we in maths pronounce that Greek letter, pi, and the thing that we eat, pie, they just sound the same. So where did it come from? It didn't actually come from Greek mathematicians. Pi itself was known before the Greek mathematicians. It was known to the Egyptians and the Babylonians. But the fact that the circumference of the circle was related to the radius in that way. The choice of the symbol traces back to the 18th century. The P is not the fact that it's the pi and P are the same letter translated from Greek to our other alphabet, because it was for perimeter. But it was perimeter originally. Perimeter divided by diameter was the thing that they were quantifying and used this symbol, but they used the pi bit for the perimeter and the D in the bottom, and they wrote it as a fraction all the time and eventually got sick of it and dropped the fraction bit and just wrote the P symbol, the pi, to mean that thing. I've heard people tell me that no, you don't say pi in Greek, you say P. Which would give us all sorts of different things for Pi Day. But in fact, I listened to it on YouTube and I listened over and over again. It's more like P than P. Yeah. So depending on how you pronounce pecan, whether you say pecan or pecan, like there's a pecan pie for Pi Day. It's been put on a plate that's got the pie around it. Now, where did I source that photograph from? Well, I promised you art. Well, I don't think I did, but art from the ridiculous to the sublime. So let's start with the ridiculous. Estimating pi with the culinary arts. These pies or cakes, these photos are all taken from something that in the UK is called the Maths Jam, where people get together and do recreational maths, and they have a bake-off, the Great Bake-Off, which is sort of a play on the Great British Bake-Off, and people make cakes that illustrate mathematics, and here are 2 of them that are related to pi. The one on the left is called Buffon's Needle Cake. Now, I've done Buffon's Needle on Pi Day before. Buffon, he wanted to improve his odds of winning in a gambling game where you threw things on the tiled floor, and it was called the clean tile game. So when you threw in fact coins onto a square, but then you can do it with needly matchstick things onto lines. What was your probability that the thing you were throwing actually crossed the line on the floor or not. And it turns out that's related to pi. The probability is related to pi. And since then, people have used that as the basis for a method of estimating pi, which is not what Buffon wanted to do. He just wanted to win at gambling. So the way this cake works, though, you can see the lines. The person who baked the cake has put short sticks of pretzel in the cake mix. And you cut this, what they wanted people to do, it was like not just a bake-off, but it was participatory. You cut through it and you counted how many pretzels you'd cut and you wrote it down on a piece of paper. And by the end of the afternoon, they had an estimate of pi. You don't get a very good one very fast with Buffon's needle. All right, the one on the other one is again a method of estimating pi. So orange peel has been scattered onto the circle. And you can count how many pieces of orange peel have landed on the circle. It's got to be proportional to the area. So that number is proportional to pi r squared. And then again, using pretzels, you might be able to see there's a square marked out on the cake. And that that's the length of the square is the side lengths are r. So that's r squared. And you can count the number of pieces of orange peel that have landed inside the square, and then divide the first number by the second number and you'll get an estimate for pi. And again, I'm not suspecting that it's a very good estimate. All right. So that's the culinary arts, okay? Arts is a broad church. All right, we don't use that method to get all the many digits of pi that you know. So some people have come in pi t-shirts today. No one actually has this one. This is actually a photograph of a t-shirt that my husband owns. That's a series representation for pi, or pi on 4. Again, it converges very, very slowly. But there are beta series, and that's where all the many digits that are known for pi come from, the beta series, not from this particular one. There's a very funny YouTube video where Matt Parker calculates all these fractions out to many, many decimal places and adds and subtracts them all and multiplies by 4. And after all this work and many, many blackboards, he doesn't even get the first decimal place. He gets the 3 point. So I don't recommend doing that method, but it's funny if you want to watch it. He did it on Pi Day a few years ago. So we do know about the digits of pi. You can hide them all over the place. Nathan's got them hidden sort of on his t-shirt. This is a little piece that I made a few years ago when I was talking to a group of school students at the time when loom bands, and you've got to have kids who are like 14, between like 8, 9, 10 around the time of 2014 to know what these things were, maybe loom bands. And there are 10 digits from 1 to 9 plus the 0. And so 10 colors. And if you trace around starting, the black is the decimal point actually. So the green, then the point, and then you trace all around. And I've used the digits of pi to generate which colors I'm going to put there. I made it in 2014. It sadly exists no more. They're little rubber bands. They perish over time. And the property of loom bands is actually, to take us somewhere else in maths, they're Brownian links. So if one breaks, the whole thing just falls apart. So it doesn't exist anymore. But if you look on the internet, you can see people make these with beads. They knit them into scarves. Classrooms decorated with paper chains, fancy paper chains. You could do it with modular origami. There's all sorts of different ways you could hide the digits of pi using 10 colors in plain view. The ones that I thought were beautiful were tiny little seed beads, just a really, really long string of seed beads doubled around and around and around your neck. No one would know you were wearing the digits of pi, but you could. All right. I guess they're more crafts than art, but where are we going to draw the line between mathematical art and crafts? So the digits of pi, here are many, many of them. They've generated a literary form and in fact, a language called Pilish. And the literary form is called poems. So they're forms of constrained writing. So the first word can have 3 letters. The next one, 1 letter. The next one, 4 letters. The next one, 1 letter. Someone wrote a whole novel in Pilish. Or you can write a short poem. Yeah. Many of the early examples stopped when they got to 0 because they hadn't thought about what they're going to do when they got to 0. So you can find all these short examples that stop at 0. So there are different rules for Pi-lish. So one of the rules is that when you see a 0, you just do 10, right? So a word with 10 letters. But the problem is the further you go into Pi, you start to find 1s and 2s close together over and over again. And it's pretty hard in English to find lots of 1 and 2 letter words that make sense if you use them. So there are adjusted rules that you can read about if you think you would like to produce some constrained writing, if writing is your preferred art form. I'm just harping on about the constraint bit, because if you think about mathematics for a minute, and we're trying to make mathematics, art and creativity and make some links, a lot of the creative things that we do when we create new maths or when we make a new proof is we are being creative, but within constraints. Now, this isn't meant to be mathematical art. This is actually just, I took it from Math World. It's black and white image that helps us to visualize what it means for pi to be an irrational number. So if we, like the 22/7, people say, oh, pi is like 22/7, or if they've had a really bad maths teacher, they'll tell you that pi is 22/7. Pi, the digits don't repeat. Now, the black and the white, odds and even, we can just take it as odds and evens, parity 0, parity 1, if you express the numbers, the digits in binary. So on the right, this is what happens if you expand 22/7, it repeats every 6 digits. So you get this very regular pattern. If you actually use the digits of pi, you get what's on the left. So if mosaic is your thing, or patchwork is your thing, or you could tile your bathroom, I don't know, but there are ways that you could visualize the irrationality of pi using squares. Yeah. I don't know where that it didn't say where it started from. Yeah, I agree. I couldn't work out whether 1, 4, 1, 5, like which part. No, we can write to Eric, right? Yeah. Yeah. All right. So this is a piece that I made, and we'll talk about the distribution of the digits of pi. And the piece is here today. So the digits of pi are believed to be uniformly distributed. What that means, it hasn't been proved. It's believed. No one's come up with it. No one thinks they're anything else, but it hasn't been proved. So what it means is that not if you take a short list, but if you take a really long list of the digits of pi and you count how many times 0 is there and 1 is there and 2 is there, they should all be the same. Fraction of them should be represented. So Judy Ann very kindly said that I'm an artist. The main thing that I do is fibre art, and most recently it's this form of art, which is called hitamazashi. It's a kind of Japanese stitching, constrained stitching. Basically, it's just running stitch on the square lattice. So the rows and columns that have been made in that piece, do all the rows first and then do all the columns. And then because I wanted to sort of pick something out, I've actually gone over a section of it with red thread. But the black lines were created horizontal first, vertical next, using that property of the digits of pi, odd, even, odd, odd. Because when you do running stitch, which is over and under and over and under, a bit like weaving, either every row of stitching starts on the top or it starts on the bottom. There's only 2 possibilities. You either start stitching like this, or you start stitching like that. Only 2 states for every row and column. And that piece is called corner percolation, because some mathematicians, when I started writing about this in places, some mathematicians saw it, and other mathematicians saw it, and they wrote a paper about it, and then they discovered that in fact this problem, or that these configurations were already known. They were known in the context called corner percolation, the idea that you take right-angled corners and place them onto a square grid. So I'm placing stitches. The original person who wrote about it was placing corners, but the configurations are the same that can result from that process if you follow some rules about how you match them up, that you can't have gaps all over the place. So it's called corner percolation, and Then I've got a little joke in there because it's done on, what color is that canvas? It's sort of like coffee color. Yes. All right. Yeah, so it's a form of constrained fibre art that I do. And I did bring that piece today that you can look at close up. Obviously not if you're in Zoom. Please don't pass it around, Julia. No. Oh, no, it's just sitting there. You can have a look at it. All right. Let's get back to pi. Pi and circles. Let's think about pi and triangles for a minute. We don't always think about pi and triangles. Well, here's a picture that you don't see very often. I don't think you see this picture often enough, right? Usually what you see is the unit circle and you see it broken up. Here's pi on 2. Here's pi on 3. Here's pi on 6. And you can still leave high school maths and really have no idea how big a radian is, right? No idea. But if you look at this picture, like degrees are little things and radians are great big chunky things. They're big, right? There's only around a circle 2 pi of them. So just over 6 radians in a circle. All right. So, yeah, just under 3 of them are just under 180 degrees. So that's what it means when you say that the radian is the angle subtended by an arc of a circle with the same length as the radius. In other words, you take the radius, piece of string as long as the radius, you pick it up, you wrap it around the circle, and then where it starts and finishes, you trace lines back to the origin, and that angle in there is a radian. And we measure them. It's an alternative to using degrees. I wasn't going to tell this story. I once had a student tell me that pi was rational. You know why pi is rational? Because of 180. All right, pi is 180. Yeah, 180 degrees. All right. So what's pi got to do with triangles? Well, that's exactly what pi has to do with triangles, because we all know that the sum of angles in a triangle is 180 degrees. But if we're going to talk in radians, the sum of angles in a triangle is pi, isn't it? Only in Euclidean geometry, all right? When we're on the plane, Euclidean geometry, where a straight line is the shortest distance between 2 points. Well, the straight line is always the shortest distance between 2 points. If you've got a rule, I forgot to bring a nice big piece of white paper off using the wrapping paper. If you've got a ruler and 2 points and you rule the line between the 2 points, that will find you the shortest distance. However, if you don't have a ruler, you can always fold the paper and that will make a straight line for you. Now that's something we need to remember, all right? That will make a straight line, shortest distance between 2 points. It would be better if we called that a geodesic, shortest distance between 2 points, because we're going to need that in a moment. Because what happens when we go away from Euclidean geometry to another geometry, the non-Euclidean geometries? So the first one we'll talk about is the sphere. I brought a very small sphere with me, I'm sorry. But it's a sphere with which we're all fairly familiar. So I think you'll be able to work out what I'm talking about. So we're going to draw a triangle on the sphere. The simplest way we're going to do this is we're going to start at the North Pole and we're going to draw down to the equator. Then we're going to travel a little way along the equator and then we're going to travel back up to the North Pole. And we've drawn a triangle because we traveled on what are called great circles all the time. Yeah. So we've drawn a triangle. So now let's work out what the angle sum is. Well, when we came down from the North Pole and hit the equator, we hit it at 90 degrees. And the other one that went from here down to the equator, 90 degrees. I don't even care what I drew in here because I've already got 2 90s, 180. There are definitely more than 180 degrees in this triangle because I drew it on the sphere. So in spherical geometry, the angle sum in a triangle is greater than pi. It's equal to pi when I'm on Euclidean geometry. So what about hyperbolic geometry? Now, hyperbolic geometry is sort of like, so if a sphere has positive curvature, hyperbolic geometry has curvature, but a different kind of curvature. It has what we call negative curvature. And this is the cover of the Mathematical Intelligencer. It's a picture of 3 pieces of crochet, not particularly functional crochet. You probably couldn't use them as a mattress, like part of a blanket. You couldn't use them as a doily, but you can use them to teach deep mathematics that people were struggling to teach before, or at least struggling to imagine before. It's hyperbolic geometry. It's got negative curvature. So a Latvian American mathematician, her name is Dana Tamina, she saw a paper model that someone was using for teaching this. Now, this paper model had been constructed very carefully from tiny little annuli stuck together, very, very fragile. Absolutely, you couldn't draw on it. Absolutely, you couldn't pass it around the class. And absolutely, you couldn't make geodesics on it. Because remember, a geodesic, I got them by folding my piece of paper. If you've got a really fragile paper model that took hours and hours to make, you're not going to just like start drawing on it and folding it. But I'm very happy to pick up a piece of hyperbolic crochet and fold it. And she realized that the instructions for sticking together these tiny little rings of paper, that's exactly what you do when you crochet. You just make a ring of stitches and then you make another ring of stitches joined onto it. And that's how you put crochet together. That's how you build it. So I'm glad we turned the lights off. On the purple piece, and I did also bring a green piece, which is over there, which you can pass around, Judy, and I don't mind if the green piece of crochet gets passed around. There's a triangle on there. So there are 3 lines that were obtained by folding the piece of hyperbolic crochet 3 times. And they are geodesics on the hyperbolic surface. They don't look straight, but they don't look straight because we're so used to living in Euclidean geometry. We think straight is not what it is if you really live in hyperbolic geometry. And you can see the corners as you go out to the corners of this triangle. These lines, which are the geodesics, these curved lines, which are geodesics, which are actually straight lines in hyperbolic geometry, they're going to meet each other at quite small angles. So when you add those 3 angles together, you're not going to get to pi. It's going to be smaller than that. And that's what's true about hyperbolic geometry. So really, from her background as a Latvian woman who had grown up in the middle part of the 20th century, she had learnt to crochet. She had brought this skill that she had into her mathematics research and teaching. And yeah, it's a mathematical fibre art form that has grown out of her desire to make a physical mathematical model of something for teaching purposes or for learning purposes or for her own instruction. She gave seminars about it in many different universities around America, and funny things would happen. Like she was at a conference and she gave a talk the first day, and when she came back the second day, a whole lot of mathematicians had been to the local Spotlight store and got themselves a crochet hook and a ball of yarn and wanted to be shown how to do it. And a professor who had taught this all his career, had looked at her model, and he goes, oh, that's what this bit looks like. So just amazing insights from her craft skill. I made a piece of this. It's over there. Crochet is an unconstrained fibre form. It looks different every time I put it down. The Australian summer, which my husband calls the hyperbolic cabbage. There it is. I was given 40 minutes, so I'm doing.
You're doing really fine.
Yeah, I know. We're going to be out of here before 5 o'clock, I have a feeling.
Yeah.
So this is a piece that was an entry in the very first CARMA-MATRIX Art poster. If Judy Ann's allowed to like the hyperbolic skirt the best, I think this is a beautiful piece of art. it doesn't photograph particularly well. I guess that would be the thing about it. So it is made out of circles. So if you don't want to ice a cake or thread some beads or tile your bathroom or make a piece of crochet, maybe you would like to make something out of paper. So it's cut and folded. Its name means white circles. It might remind you maybe of the Opera House. I don't know. But there's something about paper art which is different from paper sculpture, which to me is quite different from sculpture with bronze or stone or something. It's so fragile. It looks fleeting, doesn't it? I think it's very, very beautiful. And to photograph white on white on white, you can actually see the shadow where it falls on the glass plate and everything. So it's not just a nice artwork, it's actually also a really nice photo. And photography might be your creative form of expression. So it was in the first year, and I've written CARMA there quite deliberately because in the first year, and I think the second year, not sure at what point, it was just a CARMA event and it hadn't yet been associated with Matrix. Judy Ann didn't mention that part of the Matrix connection is that artworks are actually exhibited at Matrix after the competition is over. And yeah, we're here to launch the competition as it goes into its 6th year. Here are some other places that you might find inspiration for mathematical art. And if you look at the posters in the hallway, I walked up the hallway between the tea room and here, you will see many beautiful images that have come out of people's research that in their own right, they're beautiful. Yeah, they could be considered to be artwork. I think the input here was probably around the choice of colors, the choice of scale. You can have a look at the tops that Judy Ann and Matt are both wearing. Again, images that came out of Matt's research that are beautiful in their own right with the choice of coloring, right? You chose the colors for the
Colors were chosen after the creation because there was a competition for the one of the special interest groups. So this was chosen to look good. We had another coloring which was more mathematically informative, but didn't look.
So there you go. So you could take a piece of research, recolor it, and make it more artistic. There are many ways that you can express your creativity. Yeah. So this artwork, I think it maybe got a second prize in 2021. So Bethany Caldwell was the PhD student, and the other two are the academics who were her supervisors. And she also, I believe, won an award for visualizing research at the University of South Australia for this image. Drawing and painting. So this is a piece that I just came across this week. I came across it on Blue Sky. Elka and I have started following each other. This is called There Will Be Light. And it's a depiction, an accurate depiction of what each of Maxwell's equations tell us. I won't attempt to explain which bit is which or what Maxwell's equations are or what they tell us, but this is a piece of art where you can see curves with arrows on them which are telling you something about flux. You can see radiating things, swirling things. Yeah, so this is her artwork that represents Maxwell's equations. And yeah, in drawing and painting, this might be another form of mathematical art that you might want to engage in. Where do you find mathematical art if you're not in the room talking to me? There's a lot on social media on Blue Sky. If you hashtag math art, S is usually not there. It's usually math art. At the minute, I'm engaged in something called Math Art March, where there's a prompt every day of the month, a mathematical prompt, and people are posting pieces of mathematical art to those prompts. The prompt for today is irrational, by the way. And then there is the International Bridges Conference and the Journal of Mathematics and the Arts, which grew out of the Bridges Conference. So you saw a little piece, not a little piece, it's a triptych, Kate Smith-Miles' triptych about neg entropy. The article that she wrote about that appeared in the Journal of Mathematics and the Arts. The Bridges Conference truly does build bridges between artists, mathematicians, and people who consider themselves to be mathematical artists. And there is a group of us who very much wish to bring this conference to Australia. It's never been to Australia. It's typically held in North America. So there's a group of us who are big push to lift the profile of mathematical art in Australia so that we can launch, put in a expression of interest to bring the conference. Bridges 2027 is our goal. Yeah, so I thought I would mention that. Yeah. And then, of course, I mentioned Blue Sky, but also Instagram. A lot of mathematical artists will have something on Instagram that you could follow them and see what they're doing. So why do people do mathematical art? This just came up yesterday. I always think that David Riemann, like the spelling that's correct, all right? But wouldn't it be funny if he made a Riemann surface? Like, wouldn't it be? Anyway, actually, Peter's here. So Peter has taught complex analysis at La Trobe, and you actually had students building physical Riemann surfaces, which were, in fact, an artifact. And some of them really you could have called a piece of art. Yeah.
Yes,
Yeah.
Still in the forest project.
Yeah, a project to actually make something that visualizes what they learn in complex analysis. But this is what David says. I like mathematical art because it can foster a dialogue that can reach people who have limited mathematical training. A proof by induction or a textbook. They only speak to people who already understand it. I want everyone to see that mathematics is a gift for all and not just for an elite few. So, what do you do? Well, look at this. Can you get some feeling for what I do? What does it mean to say that pi is irrational? What does it mean to say that something is random? Yeah. Maybe you can illustrate it or visualize it in a way that is different, that might speak to someone who speaks a different version of communication. I was at did I say I was at an art opening yesterday evening, which was completely different. It was at the Olivia Newton-John Centre. It was a woman who had grown into art after breast cancer through art therapy. And I'm listening to people talking about art and I'm thinking none of this is what we do in mathematical art, until one of the speakers said art talks to people. And I thought, oh, that's right. Yeah, art talks to people. We're good. So here is another piece that I think is really nice, 2022. I believe this piece won. I think it's just so whimsical. It's a depiction of the Navier-Stokes equation. So what does that mean? Well, the Navier-Stokes equations govern fluid flow, essentially. So you can see vortices in there, whirlpools, you can see splashes, you can see bubbles, all those kind of things are governed by the Navier-Stokes equation. And here they are in one whimsical, beautiful image, aren't they? Yeah. So what can we say about mathematics, art, and creativity, and how do we connect mathematics to art? Well, working creatively within constraints, I already mentioned that, yeah? Thinking creatively and coming up with a new argument, creating a piece when you work in something like you're writing a poem or you're stitching Hidemazashi, that constraint and still being creative. Both artists, mathematicians, and mathematical artists want to visualize things and represent them for other people, whether that be an idea or a phenomenon. So hopefully you've come on this evening stroll with me. We started with cakes and loom bands, and we've finished up with, what I think are things that you'd probably be very happy to put on your wall rather than whatever you do with a cake. You've finished eating it. All right, thank you very much.
Thank you so much, Catherine, and momentarily we'll open for questions. First, I'll just comment that we're taking the speaker to dinner somewhere on Lygon Street after this, so if anyone wants to come along, just sort of mill around at the end and we'll wander off somewhere. And also, how do I direct questions to the online people, Paul and Dom?
I'll read. If there are any questions here, I can.
Oh, I did. Yeah. Okay. So I should tell you well, this is now going around the room. As well as Australian summer and an actual piece of Hitamazashi, there's an inspection copy of my book, which just came out recently, which is about the mathematics of Hitamazashi. And there are some postcards that have got the details about the book, and you're very welcome to take the postcard. On the back, you'll find a little square grid. Why did I put a grid on the back of the postcard? That's so you can draw your own little over and under, back and forward lines. Oh, yeah, that's the book.
Putting it in
Oh, it's a
the
picture.
shop.
All right. Yeah. So, questions? Yeah. Julianne, did you want to?
Yeah.
Let me just. Or comment. I guess comments. You know,
Questions,
comments rather than
thoughts,
questions.
Associations.
Mel.
Maths Jam runs in a lot of different cities around the world. Melbourne's one is on next Tuesday.
Whoa. Hey, there you go. Maths Jam.
So next
Jam and
Tuesday,
vibing.
yeah.
Melville, 5-minute walk to Melbourne Central Station. And probably yeah, there's a puzzle sheet. And it's run by different people in each city, but it's got a centralized puzzle sheet that everyone does each month.
Fabulous. So is that an open invitation? And you just need to rock up. You don't need to.
There's a meet up form for the Melbourne one. I think maybe the rest of Australia's ones as well. I think it's been Sydney.
So like math, you just Google Maths Jam. Yeah.
It'll show you all the ones going on.
Wonderful.
There was.
Yeah.
Yeah.
Are there applications for the hyperbolic geometry, or is it just a sort of like a curiosity?
The hyperbolic geometry in general, or do you mean like hyperbolic?
Yeah, well, what you're doing with the
So no, this is just, I made it as an artwork. Dana originally made them to teach with, but then has become a mathematical artist. Look, yeah, hyperbolic geometry, it's an area, geometry is an area of mathematics, obviously, and you know, is the universe positively or negatively curved? This is an interesting question. So yeah, this is a big question. Yeah. So films? Oh,
Yeah.
yeah.
Yeah. And I know I've seen so information visualization. We've got so much information in this world, and this can be connected to that, can be close to that, can be close to that other thing, can be close to that other thing, and you just can't fit it on the flat page. But you can put it on a hyperbolic surface because there's more area that's close, and then project it down and get some useful visualizations.
So I have one from online, and it's in your piece, the Hitamazashi piece. What was the red line?
Oh, okay. Yes. So look, oh, I can go back and have a look at a picture of it. All right. So to get to percolation, so what you can see in that piece, and because it's finite, you can see some little closed loops. What has been proved is that if you make it infinitely large, all loops close. So obviously when you make a small one, they don't all close. So I have picked one of the few strings of stitches that joins up but doesn't close within that square to pick out so that your eye can find it, because it's actually quite hard to find that line. Now you can stitch a random piece like this and you would get none. Yeah, you wouldn't get any line that goes from I wanted one that went from the top to the bottom. There isn't actually one on here that goes from the top to the bottom. That was about as close as I could get, from the top to almost the bottom. But just look where it goes in the meantime. So I wanted to pick that out. And I guess, what does it mean? Well, it was actually my choice as the person who stitched it to do that. And I chose to do it in red, and I chose that part to do. And then I had to exercise my judgment, not as a mathematician, but as someone who was making a piece of stitching. Did I want to do another one as well, or was one enough? So I stopped and looked at it and I decided that one was enough. So that's the one that I did.
That's all that artwork there on your home.
Oh, yes. I'd hardly call that an artwork, but yeah, on there, yeah.
Don't I use parallel lines or?
No, so they are not parallel lines. I do have another one, which is stitched, which I didn't bring. Because yes, so that's a point about hyperbolic geometry. So on a in Euclidean geometry, parallel lines, if you've got two lines that don't meet and you draw another one that doesn't meet the first one, it also won't meet the second one. Parallel lines never meet. If you are on the hyperbolic surface, you draw the first line, the geodesic, fold it. You can draw two more which don't cross the first one. So they are parallel to the first one, but they cross each other. Yeah. So that's hyperbolic geometry is just different, right? So no, those aren't parallel lines. But if I brought the brown one where I had that on there, but that wasn't part of what I wanted to say today. So I only brought the triangle one. Sorry. Yeah. It was a good question about, because that is one of the facts about hyperbolic geometry. And then on the sphere, so if we've got in Euclidean geometry, parallel lines don't meet, and in hyperbolic geometry, they can meet. What happens on the sphere? Well, on the sphere, like everything is really, what's the concept? Every line meets every line. So are they parallel or not? No parallel, no such thing. Yeah. So the three geometries, the angle sums are different and that property about parallel lines is different. And that's in fact why they realized they needed new geometries, because the fifth postulate about parallel lines didn't fit. And once they threw that out and said, oh, well, parallel lines might be able to meet, that came up with the new geometries and it made the rest of geometry work, if that makes sense, the other postulates work. Yeah, but that's another talk. So Jan asked me, was this a talk I'd given before or was this a different talk? That bit's in the other talk where I stole some of the slides from. I'm aware that some people probably got to be somewhere at 5, so
Yes,
we
so
might
we've
just
got
round it off
5
and people
to-
can talk
Yeah.
if they want to.
Any
And it's
last
Friday afternoon.
burning questions? Because if not, we can go for a wander, a perambulation, a randomish walk down.
Yeah, so
White
I
Street.
just want to repeat that the leading artwork.
Yeah, yes, absolutely.
Will be exhibited permanently. However, like all that. Just want to get the bit down.
Thank you. Yeah.
I meant to mention that at the
Yeah,
start
so
too.
Matrix came on board, I think, in your 3rd or 4th year, right?
Third, I
Yeah.
think. Yes. Yep. And the artworks are just shown at the Creswick facility, and the Creswick facility hosts lots of amazing events. So get seen at all those amazing events, and also in the Creswick News. You were in the Creswick News one day, I remember. So it really does reach into the public and the broader population. Thank you everyone for coming. Thank you again amazingly to Katherine. Thank you to Dom and to Jan and to Tom for all your work putting, and Paul.
Yeah.
For putting this together, and let's thank all of these people one more time, and then